Swayam Prabha. Digital India. Educated India.
Dear students, in our last lecture, we learned a few fundamental concepts of probability. We also looked into few definitions that are very important to our discussions going forward in risk, reliability, and resilience. We also looked into two examples to motivate how mathematics and probability can inform real world decision making. Especially when I talked about that coffer dam example, this is of course a textbook problem with all the simpler values that I included in the example. But these are the challenges often faced by engineers across the globe whenever constructions are being done in riverine settings. Hence, that essentially tells us how important understanding these things are for us to translate our mathematical intuition or understanding to decision making. So, continuing the same thread of thoughts, let us continue our discussion on analytical models of random phenomena, where we are essentially going to talk about mass functions, distribution functions, both probability as well as cumulative. So, in this particular course, we will introduce, in this particular lecture, we will introduce you to the term called as random variables and how to deal with random variables mathematically, probability distributions of random variables, and what are the descriptors of random variables. And in this lecture, we will focus on central tendencies, and in subsequent lectures, we will talk about variability of random variables. When we talk about random variable, in last lecture, we talked about something called as event, and we said that probability or x greater than equal to x is if we are talking about flood water levels, and we say that if depth in a river exceeds some threshold 5 feet, we call that as a flood. That was an event. Now, if we have to express this same depth greater than 5 feet mathematically, we will make use of random variables, and we will say that, let's say that capital X in this case is a random variable, and whenever it is exceeded by certain value, that is capital X greater than small x here, this distinction is very, very important, because random variables would be represented in these capital letters and the values that they can assume would be represented in these small letters. And when we write this mathematically, we are essentially converting our Venn diagrams into a number line representation that can take values from minus infinity to infinity. So, from visual depiction, it is translation to a number line representation. And as soon as we go into number line representation, we become much more powerful mathematically to do differentiation, integration, summation much more easily than what we were able to do just using the sets or concepts of set theory. So, in another word, random variable can also be thought of as a mapping function that transforms event from possibility space. This was a possibility space. If you recall, we said that this was S, this particular event was A, this particular event was B. So all these were possibilities of A, B's in sample space S. But when we talk about random variables, everything now becomes discussion around the number, that is x taking value greater than x, capital X taking value less than equal to x, or it is taking exactly value equal to a particular number. And once we translate these numbers to number line, we can measure the probabilities associated with these random variables using rules of probability, which are often encapsulated in probability distributions. Before we go to probability distribution functions, we have been already talking about probability of x greater than equal to x, x less than equal to x. In this domain of random variables, this mathematical representation that x taking value less than certain threshold has a special name, what we call as cumulative distribution function. Why this is called as cumulative? Because when we are talking about probability of capital X less than equal to small x, we are essentially talking about all possible values of x from minus infinity to point of interest. If we are dealing with continuous random variables like flood levels, we can essentially integrate them. However, if we are in the discrete domain where random variables can only take values 1, 2, 3, 4 and so on, and of course negative values allowed, this can take value, this would be become summation from minus infinity to x of px. Now this summation is also accumulation or cumulative value of this particular function px, as x takes value from minus infinity to x, and hence the name cumulative distribution function. Now this cumulative distribution function have few very important properties that we should always keep in mind before we qualify any function fx to be called as a CDF or cumulative distribution function. First one of it is that value of cumulative distribution function cannot exceed 1 and it cannot be less than 0. So its range is restricted between 0 and 1, both included. It is a non-decreasing function, that is, it cannot have a negative slope at any point. Its slope can be 0, its slope can be positive, but it cannot be negative. And hence, because as I said, its value is between 0 to 1. And if I'm talking about floods, for example, if I talk about probability of flood less than equal to 5 feet, I can say that f of 5 is going to be certain number, let us say 0.3. If I say f of 10, I am essentially talking about minus infinity to 10 fx dx. This can also be written as minus infinity to 5 fx dx plus 5 to 10 fx dx, because I can always split my limits of integral from minus infinity to 5 and 5 to 10. And if you focus on this information, that is minus infinity to 5 fx dx, this is already contained in f of 5 and probabilities cannot take negative value. Hence, f of 10 is equal to f of 5 plus some positive value. Hence, CDFs are always increasing function. Even if f of x dx 5 to 10 takes the value of 0, even if the second term is reduced to 0, this value of fx never decreases, as a result of which we call these as monotonically increasing or non-decreasing function. Also, When x tends to infinity, these values of probability CDFs tends to 1 because flood level will always be less than equal to infinity. Hence, probability of having a flood level less than equal to infinity is equal to 1, and that's essentially what is contained in the definition of cumulative distribution function. Similarly, as x tends to minus infinity, in case of floods, minus infinity value is not possible, but let us consider any other phenomena where x can assume value up to minus infinity. Uh, you cannot have the integral equal to 0 whenever we are summing up a non-decreasing function. Hence, the lower limit of a CDF comes out to be 0 by virtue of the definition, or we are essentially quantifying the way we are quantifying or defining the cumulative distribution function. So, in summary, the lower limit of CDF is 0, upper limit is 1. Whenever we are talking about CDFs, it's basically probability of a random variable taking value from minus infinity to point of interest. Another related concept that spawns from CDFs is probability mass functions. Probability mass functions are typically applicable to discrete random variables. That is, when variable can only take values such as 1, 2, 3, as we have already discussed. In case of coin toss, we may say that head is equal to 1 and tail is equal to 0. So this is one of the mappings that I initially mentioned, that role of random variable is to map from possibility space to real number space. So I have mapped head to 1 and tail to 0. So I have done basically, I have converted the possibility into a random variable. So when we talk about probability mass function, we are essentially talking about point probability of random variable taking value x equal to 0, x equal to 1, x equal to 2, and so on. And on y-axis, we will have probability associated with that particular x. We call this as a mass function because they essentially have spikes at the value of interest between two discrete values. There is nothing occupied. Hence, entire mass is concentrated at certain points, and hence the name probability mass functions. And they, again, by the definition, probability cannot be less than 0, and they assume the value between 0 to 1, as probability of individual events cannot also exceed 1. And also, when summed over entire domain of values of x, they again conform to the behavior exhibited by cumulative distribution functions, and they also sum to 1. Now, when we talk about mass functions, we were essentially talking about spikes at certain points. But when we talk about probability density function, now between 2 points, let us say x1 and x2, entire region would be occupied by certain probabilities, because now we are talking about continuous variables. Again, on y-axis we will have px, on x-axis we will have x, and if we are interested in probability of x between x1 and x2, we can simply do the integration or summation by parts of this region of interest and calculate the probabilities that we are interested in. And this function that I have just drawn here is called as probability distribution function, and in our future discussions we will simply call it as a PDF, and it describes likelihood of a continuous random variable x taking on specific value x. Again, all the conditions that we apply to PMF also apply to PDFs with certain adaptations. For example, values of CDF at each point is greater than equal to 0. When summed from minus infinity to infinity, that is over its entire domain, or when we are talking about continuous variables, summation translate to integration. So integration from minus infinity to infinity for fx should yield us value of 1. And if we are interested in probability of random variable x taking value between a and b, this integration would be done within the limits of a to b for this fx dx. One distinction that we should notice here, because whatever books, textbooks, examples we will refer to, they would simply use that, assuming we are familiar with that. Whenever we write anything as f of x, that is capital F of x, we are essentially talking about cumulative distribution functions. When we talk about small f of x, we are essentially talking about probability distribution functions. Also, one distinction that exists between PDFs and PMFs is that PMFs can be used to determine the point probabilities, whereas PDFs cannot be used to determine point probabilities because they represent the density and not absolute probabilities in probability theory. We'll come back to that later, because sometimes you may see PDF value greater than 1 and you may see, oh, it has violated the rules of PDFs, but that is not true. You cannot use PDFs to determine probabilities of individual points, unlike PMFs. Now we have introduced two concepts, PDFs and CDFs. We already said we will represent CDF by capital F, PDF by small f. Mathematically, if we integrate a PDF from minus infinity to point x, that is point of interest, we are essentially deriving the CDF. Conversely, given the CDF, if we differentiate that particular CDF with respect to x, we are going for PDF. That is, integration of PDF up to point x from minus infinity to a point of interest gives us a cumulative distribution function, and inverse of integration, that is differentiation, help us retrieve back the underlying PDF of a random variable. And these two transformations are very helpful because we may only be specified one, and based on that we can always find the functional form of the other or the numerical form of the other and keep on quantifying the risks and uncertainties associated with the problem. Again, as I stressed before, that PDF is not a probability, but it's a probability density. Hence, small f x equal to x, it has no physical significance. It is just a mathematical quantity that indicates density of a probability and not absolute probability in probability theory. Now, two other observations for completeness of discussion. Just like we wrote when we were talking about PDFs that if we are interested to determine what is the probability x will take value between a and b, we simply integrate from a to b and whatever function or PDF we have for our random variable. In our future discussions, this fx will take well-defined mathematical, specifically in many cases it would look like an exponential function. So fx would have very less mystery associated with it as we introduce some useful probability distribution functions. But as of now, think of it, it's a mathematical function that is known to us. Hence, if given fx dx and a and b specified, we can really calculate probabilities of x between any two values a and b. For discrete random variable, this formulation takes the form of summation, and it is written as x equal to a plus 1 to b, because if you notice here, x is greater than a and less than equal to b. Using same concept, I can also write probability of x less than equal to b, where x now takes value a to b, and again px goes into summation. I can also write minus infinity to x to b. This would take value minus infinity to b, px, and this again becomes CDF. So once we understand how PDFs and CDFs are defined, we can really go from one form to another without thinking about it twice. Let us reinforce this concept with help of an example. Here, let us say X is the number of floods in a particular year in a given region. Probability of 0 floods is given to us as 0.5. Probability of 1 flood is given as 1, 2 floods as 2, and 3 floods as 0.05. It is asked to determine the CDF. Now, if we talk about fx of 0, when x takes value of 0, we are essentially interested in probability of x less than equal to 0. That is either 0 flood or less than 0 flood. Now, less than 0 flood cannot happen. So, this simply takes the value same as px equal px 0. When we talk about fx equal to 1, we are essentially talking about less than or equal to 1 floods. That means 0 floods or 1 flood. So it becomes 0.5 plus 0.3, which is 0.8. Now, probability of 2 floods are given as 0.15. If we have to tell what is CDF, capital F of 2, we are essentially talking about 0 flood, 1 flood, or 2 flood. So it becomes 0.95, and F of 3 essentially becomes 0.95 plus 0.05 equal to 1. Now, if you see here, all our conditions of CDFs are met. No value is exceeding 1, no value is less than equal to 0. This is monotonically increasing function, and if we plot this, we are essentially going from 0.5 to 0.8. From 0.8, we are going to 0.95, and then we are going to 1. We call this as fx. For different values of x, we have determined the full behavior of our CDF. So that was a case when number of floods were being monitored, which is a discrete random variable. When we talk about continuous random variable, let us say y be the elevation of flood in meter at a given point, then PDF can be written in as f of y is equal to 0.2y. How this 0.2y comes into picture? Perhaps it came from data, or it was already known. We already talked about that in estimates of probability. This is a very simplified probability distribution function, but when we will talk about normal distributions or exponential distribution, this mathematical form may become a bit cumbersome, bit tedious to look at, but the concept will essentially remain the same. That is, from here we can derive CDFs either numerically, analytically, or computationally, but this becomes the fundamental block. Now, if you see here, it says that f of y is 0.2y. Now, based on this, I can answer a lot of questions. For example, if I have to tell what is the probability that y would be less than 3 and greater than 1, I have to simply say that, okay, I will integrate it from 1 to 3, f of y dy. I know this function exactly, so I will just substitute f of y as 0.2y dy. When I integrate it, it becomes 0.2 y square by 2, and when I substitute the limits, I have determined what are the chances that flood levels will be between 1 feet and 3 feet, or 1 meter and 3 meter, and so on. I can also use this particular information to determine what is probability that y would be greater than equal to 5. Now, if you see here, the otherwise condition says that this PDF does not exist in range greater than 5. So the answer simply comes by looking at the distribution or functional form of this PDF carefully as 0, because probability of flood levels not exceeding probability of flood level exceeding 5 meter is equal to 0. This also tells me that probability that flood level would be less than equal to 5 is equal to 1, because if probability of x greater than something equal to 0, probability of x less than same value equal to 1, because ultimately sum over entire sample space has to be 1. So again, the point here is same simple definitions coming together to answer questions of interest in context of risk hazards, and in this specific case about the flood levels. So as I said, you can go from PDF to CDF by simply integrating, and for this particular example, if we integrate it from in its domain, we get the CDF as 0.1 y square, and Fy becomes 1 for y greater than for y greater than 5, because flood levels are always going to be less than 5 meter. Hence, probability of x less than equal to 10 is going to 1, which is essentially encapsulated in the second equation that I just highlight. Now, when we talk about random variables, we talk about the functions, and these particular functions can take different form. They can have peak or at some point. They may be symmetrical around their central point, or they may be skewed. They may be thin-tailed, or they may have much fatter tail. So these functional forms, as long as they abide by the rules or and rules of probability, they can take different functional forms. So important question is how to summarize them, how to come up with the statistical summary of these distribution functions, and that is where central tendencies come into picture. Whenever we talk about central tendencies, we essentially talk about three measures. First being mean, second being median, and third being mode. Mean is simply average of a particular random variable. So let us say we made observation of flood depths in a river. Values were 1, 1.2, 1.3. We only have 3 samples. Mean would be simply 1 plus 1.2 plus 1.3 divided by 3. In probability, we will also call this mean as expected value of random variable, and it would be often represented as expected value of x or simply mu. But it essentially represents the average or central value of random variable. When we talk about discrete random variable with known probability mass function of px, the expectation of x or mean is simply x multiplied by px and its summation over all possible values of x. This also stems from the fact that this is more like the weighted summation. If you recall, I used a similar terminology when I talked about total probability theory. That is, we are doing weighted summation. X may take a very high value, but its probability of occurrence is very low. So the expectation has to be modulated to take care of both product of X and its probability of occurrence. And that is why expectation of X is X px summed over entire domain. When we talk about continuous variables, the expectation again can be written using same analogy as what we wrote for discrete random variables, but instead of summation, we go for integration over entire domain of x. For generalization, we write it as minus infinity to infinity fx into x, and of course dx, because we are talking about the integration here. But this is what I was also doing when I was calculating expected costs. I knew exact functional forms in that particular case, but I was essentially doing expected values of x or expected value of costs when certain mean or central tendencies of number of events or flood levels were known to me while designing the coffer dam. Another important measure is median of random variable. Median simply divides the probability distribution function into two halves. That is, probability of x less than equal to median is 0.5. Similarly, on the other side, we also have 0.5. And in terms of CDF, the probability of x less than equal to median comes out to be 0.5. So the word median essentially is based on that particular value of CDF, that value of x where CDF assumes value of 0.5 or area under probability distribution function becomes 0.5. That value of x is called as median, that is often represented by m. Now, when to use mean and when to use median, we will learn eventually in our discussions with help of example that median is very much robust to outliers and mean is very sensitive to outliers. So whenever there are few extreme values in the records, we often go with measures like median. However, when we are, but the first descriptor that we always quantify in any statistical study is the mean, and then to check its robustness to outliers, we often go with the median. Another concept that we don't use much, but it is important for completeness of discussion, is mode of random variables. So mode is simply that value that gets repeated quite often or multiple times in any observation is mode of random variable. For example, if I have 1, 1.2, 1.2, 1.3, 1.5, in this case, mode is going to be 1.2. When we are talking about PDFs, if we plot PDFs like that, mode is that value of x that maximizes small fx. So in this case, if we have two peaks, this particular value which has higher magnitude than the first peak is simply going to be the mode, because this value that I just highlighted now is maximizing the value of fx and hence it is called as mode. Sometimes we hear the word bimodal distribution. That essentially means that there are two peaks occurring in the PDF being plotted and hence the name bimodal distribution comes into picture. In most of our discussions in this concept, around the concept of risk reliability, we are going to deal with unimodal distributions like normal distribution, exponential distribution, gamma distribution, generalized extreme value distributions, and all these are unimodal distributions, and that's why this concepts of mode would be of limited use in this particular course. But if you are learning any text on probability, this discussions around mode are typically part of that. Hence, it was worth mentioning it here. Finally, to conclude our discussions on probability distribution function and probability mass function, we can also generalize this concept of expectation of x to any other function, expectation of gx. If you remember, we mentioned expectation of x as x fx dx summation from minus infinity to infinity when we were talking about continuum domain, and for a discrete random variable this simply becomes summation from minus infinity to infinity x px. This same, and as I mentioned earlier, this is analogous to the weighted summation. This same understanding can be extended to any function, and we can write expected value of any function gx as integration from minus infinity to infinity. Instead of x, we can write gx fx dx, and in discrete domain it would be minus infinity to infinity gx px. Note that Gx is any function of random variable x, whereas fx deserves or reserves its special place and it meets all the properties of probability distribution function or probability mass function. Hence, we can now write expression for both discrete as well as continuous. This mathematical expression of Gx can be generalized to cost, it can be generalized to losses, it can be generalized to benefits, and hence this mathematical expression or generalizable expectation to any function Gx is very important when we will talk about costs, benefits, and losses in probabilistic sense. In our next lecture, we will introduce ourselves to a few most useful probability distribution functions and their behaviors, such as normal distribution, exponential distribution, Poisson distribution, that we already used, but we have still a long way to go to understand them fully. But we will try to cover those with help of specific examples. So previously, we understood mathematical expectation of a function gx and related it to probability distribution function or probability mass function for both continuous and discrete random variables. So a quick revision, because that's the concept we are going to use when we talk about dispersion around central tendency, specifically around mean. So if you recall, we said that for discrete random variable, when summed over entire x, expectation of gx can be written as gx into px, and when we talk about continuous random variable, same thing can be written as integration over minus infinity to infinity gx fx dx, under assumption that the functional form of f is known, which is a function of x. Now, using this particular concept, we are going to introduce a very important concept that we are going to use throughout our discussions on risk, because one essential component of risk is uncertainty. And one way to quantify uncertainty in statistics and probability is variance, which is measure of variability. And specifically, we define variance as spread or dispersion of a random variable around its mean. So what does it mean? Let us try to understand with help of an example. If we have a distribution resembling a bell-shaped curve, we will talk about what is name of this bell-shaped distribution in a short while. Then if it is mean is located, let us say at mean equal to 0. Now you see that there are certain data points which are on left side, certain data points which are on right side, and hence there is a spread. And if you have to tell visually that the two distributions that I have drawn, let us make them centered around same mean. The green one has more spread than the one that I have drawn originally. So we can say that green distribution that I have drawn here has more variability or variance. And as soon as we introduce the word variance, we are talking about dispersion around mean. By definition, variance of x is given as expectation of x minus mu square. Now you may wonder why square? Why not just expectation of x minus mu? Because we want to capture the spread on both sides. If we do not use square or norm of this particular function, in this case L2 norm, the positive dispersions or positive spreads away from the mean will cancel out the negative spreads, and hence it becomes expectation of x minus mu square rather than simply expectation of x minus mu. more. And also this is by definition that we go by expectation of x minus mu square, and also logically satisfy our requirements to measure spread on both sides, where expectation of x of course is mean. We have already discussed the three central tendencies: mean, mode, and median. And this particular definition of variance is typically the dispersion around mean or expected value of x. Now, in case of discrete random variable, if this becomes our function gx, we can write variance as gx px summed over x, as we discussed in last particular slide. Now, in this case, gx itself takes the form of x minus mu square, and hence when we substitute it here, variance of x, if x is a discrete random variable, becomes x minus mu whole square px. And similarly, for continuous random variable, we can integrate it from minus infinity to infinity, x minus mu square fx dx. Please note that whenever I am mentioning px, I am specifically talking about probability mass functions, and whenever I am using notation of fx, I am specifically talking about probability distribution functions. Now, let us try to expand it further and get ourselves familiarized with the form that you would commonly encounter in applied statistics and probability. So, first of all, we are interested in expected value of x minus mu square. Now, x minus mu whole square can be expanded as x square plus mu square minus 2x mu. And when we talk about expectation of this expanded form, this expectation has a linear property. That means we can write this as sum total of expectation of x square minus expectation of 2x mu plus expectation of mu square. We further write this as expectation of x square minus 2 mu comes out because expectation of a constant is constant itself. So we have expectation of x plus mu square, because again it's expectation of a constant value, because mean is already defined based on the samples that we have collected. And this becomes expectation of x square minus 2 mu, and expectation of x by definition itself is mu plus mu square. Hence, variance can be written as expectation of x square minus 2 mu square plus mu square, or expectation of x square minus mu square. And we know that expectation of x square, expectation of mu is in fact expectation of x. So we can write this as expectation of x whole square. So now if we can rearrange our puzzle and move these things at appropriate places, we have solved our entire puzzle of calculating the variance. So in different forms, you will encounter these different expressions. But at the end, you have to basically remember that it is expectation of x square minus expectation of x its whole square. And one common mistake that students do is that they think that expectation of x square should be equal to expectation of x whole square, which is not true. And you can try doing that you take some very simple numbers 1 2 3 4, calculate its mean, then take their squares, which become 1 4 9 and 16. This becomes essentially x square now, and calculate its mean. You would see that square of mean of 1 2 3 4 is not equal to expectation of 1 4 9 and 16. Although these are very small things that many of you may be familiar, but it's important to remember these pitfalls as we start dealing with real data, because we will implicitly assume that all these terminologies and factors are known to you. Now, to wrap up our discussions, let us look into one very simple example on the same flood data that we have been referring to again and again. And I've kept this example very simple. If you are not familiar with statistics, you can pause the video here and go through this, try it yourself. But if you are familiar with the concept, you can fast forward this simple example, because this, I would say, is 101 of stats and probability. So here question states that given the following flood data representing number of floods per year in a region over 10 years is given by, in first year we got 1 flood, in second 2, 2, 3, 4, 4, and so on. We are simply asked to calculate mean, mode, median, and variance. Now if you remember, mean is nothing but sum of everything divided by number of samples we have. We have observed this data over 10 years of time. So it would be simple: 1 plus 2 plus 2 plus 3 plus 4 plus 4 plus 4 plus 3 times 5. And we should be dividing it by 10. We should be getting estimate of mean. Now if we talk about the mode, mode is a number that gets repeated most frequently. So it would be 4 and it would be 5. Similarly, if we talk about the median, we will essentially arrange these numbers into ascending order and identify which number is exactly halfway through. Although we introduced median in terms of probability distribution function, the key thing that here is to remember 0.5, that whatever value of x separates your PDF or probability distribution function into two equal areas, that particular value x is median. So applying the same analogy, given discrete values, you can you can arrange numbers in ascending order and see that which number would fall into middle point. And once we have mean, mode, median, we can definitely calculate the variance as central tendency around the mean. Here I have used 1 by n summation xi minus mu square, because I am assuming that this is the entire population. However, this is something called as biased estimate of variance. The unbiased estimate of variance would require variance to be listed as 1 upon n minus 1. But we will come to this later. Right now, nothing to worry. Right now, we will assume that whatever form that we have studied mathematically applies. But when we will talk about biased versus unbiased estimator, we will revisit this particular point. But right now, we'll only go by the definition of concepts that we have studied and worry about biased and unbiased estimates later. Now, those who already got some time to solve this, so you can see that mean would come out to be 3.5. 4 and 5 both appeared 3 times, and hence that becomes the mode. As I said, in median, we will arrange this particular data into ascending order, and we will identify which particular number is at center. Now, interestingly, we have even number of data points here. So no data point would be at center. So what we will do, we will take average position. That is, we are going to pick up number 5 and number 6 and take average of that. And in that case, that is going to be the median of our data set. Now, if you see that mean, mode, median, they are very close to each other, even if not exactly same. Mean here comes out to be 3.5, mode comes out to be 4, and median also comes out to be 4. But all these three numbers have been derived distinctly. It just happens coincidentally or by their definitions. In many cases, that their numbers may be similar, but they are not exactly the same. But there are certain distributions that we are going to talk about where these mean, mode, medians are exactly overlapping by the way these particular distributions are defined. But we cannot take it for granted that if mean is 3.5, median has also be to be 3.5 or 4, or mode has also be to be 3.5. We have to be fairly objective whenever we are dealing with particular data. Now, once we have determined the mean, we go to the variance, which is in this case is simply 1 by n summation I from 1 to n xi minus mu square. So what we do, we take each sample and subtract mean from it and take square of that. And this further clarifies the point that I was trying to say, that if you notice, 1 is on the left side of 3.5. On the other hand, 5 is on right side of 3.5. Since we are interested in cumulative dispersion, the square terms ensure that we are not cancelling out these particular terms and they are added in square manner. And hence we end up with this variance, which is typically represented by sigma square as a number 1.875. Another related measure that we often use is standard deviation. Standard deviation is nothing but it is square root of variance, or simply sigma, and in this case it would be square root of 1.875. In engineering, we also define another term called as coefficient of variance. Coefficient of variance is normalized measure of variance, which is nothing but ratio of standard deviation to mean, or sigma divided by mean. In this case, coefficient of variance would be 1.875 divided by 3.5. So in some cases, we may be given exactly mean and sigma. In some cases, we may be given mean and coefficient of variance. In some cases, we may be given mean and sigma square. But if we have any two of these information, we can always derive the two essential parameters that are important to characterize most of the distributions that we are going to deal with in real world. So to conclude this particular discussion, in this module, we already learned about random variables, their definition and types, that is discrete and continuous, and what kind of maths apply to that. We also learned about central values, mean, mode, median, and then we familiarized ourselves with PDFs, PMFs, CDFs, that is cumulative distribution functions, and then we also did some practical applications on real flood data, that of course we represented with finite number of points, but by extension, even if you have large number of data points, most of these concepts will apply to that. In our next lecture, we are going to deal with a few commonly used distribution for random variables, and we will focus on continuous distributions first, and then we will go to discrete distributions. In continuous distribution, we are specifically going to talk about normal distribution and exponential distribution, but using the concepts, you should be able to handle any distribution that you may encounter in engineering and science world. Similarly, in discrete distribution, we will deal with two frequently encountered distribution in discussions around risk analysis, which are binomial and Poisson distribution. So most of the examples and references that we are taking in this particular lecture or throughout probability and statistics discussions are essentially taken from this excellent book on probability concepts in engineering, emphasis on applications to civil and environmental engineering, published by Wiley, and authors are Ang and Tang. I strongly recommend that that those who are interested to learn more about probability and statistics should get access to this particular book. While volume 1 deals with fundamental aspects of probability and statistics that we are going to cover, that we have already covered and also going to cover in next few lectures, volume 2 provides excellent description of applications of these concepts to risk and decision making in civil engineering. Thank you.